I'm slow, but I think it's necessary. Now, I want to discuss something called noise factor and noise figure, right? First of all, we already studied something called signal to, or did we study it? Not yet. Signal, I think we kind of mentioned before, right? Signal to noise ratio, which is SNR. What does it mean? It is the signal power, right? What you care about, like you talk in the restaurant, right? Your voice is the signal power divided by the noise power. That is the background noise. It's very noisy. If you have a large signal to noise ratio, that is great. People can hear you clearly, right? Otherwise, we run into problem. So that is the signal to noise ratio. Now, in reality, we may use amplifier. I have a signal going in, and then I have a signal going out. Now, so this is my signal. After this amplifier, it becomes very large. Great. But do not forget, I also have noise in the input. The amplifier is going to amplify the noise also. Is this okay? And unfortunately, as we already saw in the previous example, the amplifier also adds some more noise to it. Make sense? So originally, I have a signal to noise ratio. Let's say I call it input, which just equals to, maybe I don't do something really clear, but I can say that this is, let's say this is one, this is A, this is B. This signal to noise ratio is what? A divided by B. When I go to the output, I have a larger noise A dash, larger signal A dash, a larger amplified noise B dash, but I also have an extra C dash. And now the signal to noise ratio, which is the output, equals to A dash divided by B dash plus C dash. Okay? If we look at this clearly, A dash is what? A dash is just the gain times A. And B dash is just the gain times B. If you don't have C dash, the signal to noise ratio is the same after the amplifier. But unfortunately, we have C dash. So you can see that the signal to noise ratio at the output must be smaller or equals to the signal to noise ratio in the input, which makes sense. So if you keep amplifying your signal, you thought that it will be better. No, it degrades the signal to noise ratio. Then why do we still want to amplify? That is because the signal was too small to be detectable. That's why we amplify it, so we can hear. However, whenever you're amplifying something, the quality will get degraded. Okay? But we will be able to listen to the signal. But if you do too much amplification, eventually the signal to noise ratio will be degraded so much, you actually, although you can hear the signal, but it's covered by the noise. You actually cannot hear anything. Right? So that is the signal to noise ratio and the scenario. And because of this, we introduce something called noise factor. And let me call it NF here. It is equal to the signal to noise ratio of the input divided by the signal to noise ratio in the output. Basically, this is circuit specific. It means the noise factor of this circuit, it changed the signal to noise ratio by this much. Right? Again, because the signal to noise ratio at the output is smaller, this one is larger or equals to 1. Make sense? That is the signal to noise ratio. And there is another commonly used term called noise figure. Right? Some people still call it NF, so you need to make sure what they are talking about. But it's not difficult. What it tries to say is just I call it NF. Let me call it dB here. It's just equal to 10 log NF, or more specifically, 10 log of signal to noise ratio in the input divided by signal to noise ratio in the output. Basically, they are the same, except the first one is just a numerical ratio. And here, we just take the log and times 10, make it into dB. If you forgot, maybe it's a good time to review. Any value, right, for power, you will take 10 times log, and this gives you a unit of dB. Okay? For voltage, you can either do 20 log voltage square. This also gives you dB, right? Not square, sorry. No square. Voltage, right? Or you just call it 10 log V square. It gives you dB, right? Because we know the voltage square is related to the power, right? V square is just like power. So we just use 10 in front. If you take the voltage, then you will need to multiply by 20. And usually this is referred to a ratio, a reference, right? I did not say here. You need to divide it by reference power divided by reference voltage. Here we are finding the relationship between these two. And that's how you get the noise figure and noise factor. Is this okay? Any questions? So now we will go to quite a lot of math. Little bit annoying, but we need to go through that, right? We want to find the first equation about how to calculate the noise factor in a cascader circuit. Before that, we just want to look at the scenario one more time. I have a low noise amplifier here, just an amplifier, okay? Again, we model it as a noiseless circuit, but it has a noise. This noise is due to the amplifier itself, the amplifier circuit. Now, we put here, it's not here, so it is not the input referred noise at this moment. We just put it as the output. This is just like this one. Like this one. That you get at the output. Okay? So we're saying, okay, this circuit gives me this amount of output noise. That's the first thing. Let's ignore this antenna. You just know you have a source. This is the signal. You have a signal, but the signal also have an output impedance, right? Take this for granted. It cannot be ideal with no anything, right? RS, the output impedance. It has a noise, right? Not from the signal, but together with the signal, right? So this is the Vn square Rs is the thermal noise. Together with signal, but what I mean is the thermal noise due to Rs, the output impedance. If you remember earlier, we had a theory that if you have a two-port network, you look in, then the noise, right, equals to the 4 kT 4 kT 4 kT times the real part of the impedance. Do you remember this? Anyway, when you look back, when you see a real impedance of Z, right? Then the thermal noise is 4 kTRC. Here we see an impedance of Rs. So it is 4 kTRS. This is the noise, the thermal noise coming into this amplifier together with the signal. Vin is the signal, and then at the same time, because it always has this impedance, right? For example, in this type, this is an antenna. We talked about this before, because the impedance perceived by the antenna is maybe a certain value, then we will have this equivalent Rs, and this gives us the noise. When you reach this point, then you have a certain signal to noise ratio. When you reach this point, you have another signal to noise ratio. The amplifier has this gain. Now, do not forget, the amplifier also have an input impedance. The LNA. This is going to affect our noise figure also, because you will see that later. Okay? Any question about what we are setting up now? So, because of I don't have enough space, so I will start from here. The first thing I want to remind yourself is that I have this V in here. It has an output impedance of Rs. Then it goes into the amplifier, Z in. Okay, sorry, I see that my internet connection was not stable. Let me say one more time, right? This is the input impedance to LNA, and what I'm going to do is saying that, okay, now I'm looking at this part. At this place, I have a certain signal to noise ratio. Here I have another signal to noise ratio. But I just look at this part. I have V in, I have Rs, and then I look into the impedance, the amplifier, I see Z in. This is just a potential divider, right? So if the real voltage that fueled by the amplifier is V in dash, and V in dash, of course, equal to Z in divided by Rs plus Cn, potential divider, which we have studied earlier, times V in. Okay? And I call this alpha V in, just as a definition. Any questions? Any question about this? So if that is the case, what is the noise that's seen by the LNA? The noise seen by the LNA, noise seen by the LNA, I will call it Vn square Rs dash is just equal to alpha square times Vn square Rs, right? So what I'm saying is that if it is a voltage due to the potential divider effect, the LNA at this point, it only feel V in dash, which is just alpha times V in. So now if you have a noise source which is Vn squared, then your LNA only feel alpha square times Vn square bar, which is this term. Is this okay? Any questions?
Professor, where is VNRS bar?
This one?
No, not the one on the left.
This one?
Yeah, where is that on the circuit? In the circuit.
Oh. You cannot see it. It's just the amount it filled by this circuit. Because I'm talking about the power spectral density, right? So I cannot really draw it. It's just the amount of power that really goes in.
Goes in. Okay.
Yeah, of noise that goes in.
Okay.
Yeah. So So yeah, maybe I should label this as V in dash, right? So V in I can label it because at this point it's V in dash. But then here it's just saying that how much noise power you go into the circuit, so I cannot label it. Yeah, that's
Oh, after taking the impedance from the LNA.
yes, after you're taking these two ratio into account, right? For example,
Got
if
it.
the impedance is 0, you actually don't get any noise, any signal into it. Yeah, good question. Any other questions? Then I will continue, right? So I want to, let me call this A. I want to go to the part B. What is the signal to noise ratio in the input to the amplifier? As we just said, the signal is alpha V in, right? This is the signal I get. It feels this much of voltage, right? But we need to find out its power. So we need to square it. And how about the noise? And we just said, you just asked me, this one, right? So it is alpha square Vn square Rs, right? So maybe I should actually write it as V in dash square divided by Vn square dash Rs. I add the dash, right? But after all, it is equal to this. Okay, so I keep it as this. Any questions? Now, if no, then I will also ask what is the signal to noise ratio at the output. Now, this is very important. What is the signal to noise ratio in the output? What is the signal at the output? Well, the signal at the output, of course, is first you have V in times alpha. This is the input to the amplifier, right? At this point, it's V in times alpha. Give me the voltage here. Then what is the signal at the output? Times A times the gain, which is AV. Do you agree? The voltage. Everyone agree? Right? V in times alpha becomes the input to the amplifier, and then times AV becomes the total signal. But we're talking about power, so I need to square that. So this is the power of the signal. But how about the noise at the output? The noise output is exactly the same as the signal also, right? Because I have this Vn square Rs, which is the original noise due to the source impedance, and then I times alpha square. Correct? I times alpha square. Then, which is the one she just asked, this one, times alpha square. So how much goes into the noise, right? And then it gets amplified by the amplifier. If that's it, then these two can cancel. You have the same signal to noise ratio as we mentioned earlier. If your amplifier does not add any new noise, done, you are done. But it actually adds this noise. Vn square bar. Are you okay with this? So this is the gain. This is the power of the signal. This is the amplified noise from the source. And this is the extra noise due to this amplifier. Okay? So with that, I can find the noise factor. The noise factor equal to signal to noise ratio of input divided by the signal to noise ratio of the output. So it's a very big expression. Okay, so what is that? Input divided by output. So I write down the input first. I'm not going to use I actually need to use the absolute value, sorry. This is the input. Again, I do this alpha square V in square RS. This is the input, right? Signal to noise input. Then divided by output. So I just put the numerator at the bottom. Alpha square AV square, right? I'm putting this one to here. First, I copy this to here, and now I put this to here because it's division. And then multiply Vn square Rs alpha square AV square plus Vn square. Is that okay? And of course, I'm going to cancel this too. Right? Oh, I canceled the wrong. Yeah, that's right. And what do I get? You see that this term is the same as this one times this one, right? AV square, alpha square, Vn square. So this is 1 plus Vn square divided by alpha square Vn square Rs AV square. Okay, so how do we understand this? It means the noise figure equal to 1 plus the noise due to the amplifier divided by the noise of the source. And then what we call is like due to match or due to the source impedance. Alpha square is due to the source impedance matching.